Alright, so there's like a famous example that I've seen in math classes that I've taken before and seen on the internet that like you prove that zero point 0.9 repeated is equal to 1. So there's different ways to do it, I think, but one way I know how to do it is using infinite series. So again, we could take 0.99 repeated and write it as a sum of like 0.9 plus 0.09 plus 0.009, and you can see that it's geometric. It's got a first term of 0.9, and the common ratio is just 1/10. You multiply 0.9 by 1/10 to get 0.09, and so on and so forth. So that's 0.01. So if we found the sum of that, it'd be 0.9 divided by 1 minus 0.01. Sorry, not 0.01. I lied here. Sorry. That's just 0.1. And this would be 0.12. I'll turn that 0 into a big decimal. So we got 0.9 over 0.9, bing bong boom, equals 1. Pretty cool, right? So there you go. A little math fun for you. Alright, I feel this iPad falling apart as I speak, so I'm kind of rushing through this. Alright, so geometric series. So it's not showing what's on my screen. Okay, let's do one more example. I think that's all this can handle right now. So let's say you did something kind of called like an annuity. So it's like an investment that you add an amount to it every month or so. And so if you do this for 30 years, the money that you add the first day is going to gain a lot more interest than the money you add 15 years later or on the last day. So you have to keep that in mind. So not all the money is gaining the same amount of interest. So let's say in this scenario you deposit $50 each month in a savings account that pays 6% compounded monthly. What's the balance of the annuity at the end of 2 years? So if we think about this for a second, the money that you put in at the beginning would have gained 24 months of interest because that's 2 years. So 50 times 1 plus the rate, which is 0.06, compounded monthly. So every month you get 1/12 of that, so 0.5%. And that was compounded over 2 years monthly, so 12 times. So it got compounded 24 times. So I'm just going to write that as 24. Okay. Now, the money you put in the second month that you started this account would have only gotten 23 months worth of interest. So it would have been compounded 23 times because you didn't put in for 2 years, you put it in a month 2 of 24 months, so it gained 1 and 11/12 years worth of interest. All right, and then you go all the way down to the money you put in 1 month before you close the account, and that $50 only gained 1 month of interest, so only 1/12 of that 6%. Whereas this one here got 2 years worth of that 6% compounded monthly. All right, so now we're going to write this as a sum. So you could see that the variable here is the year, or like the compounding periods. So there are 24 compounding periods. That's twice 2 years over 12 months, so 12 times a year. All right, so we're going to start on the first day, the first month. So that's that $50 you put in on the last month, got 1 month of interest, and we're going to do it for 24 months because that's 2 years. All right, so this is n right here. That's what's changing each time. And our nth term formula is geometric. Our first term is not quite 50. But we're going to put a 50 there, and then times 1 plus 0.06 over 12, and we'll do it to the nth power. That's why I said it wasn't the first term. The first term would be 50 times, this number here. This is your first term. Because again, you're not going to put money in at the end when the account's done. Why would you put $50 in just to get it right back? You're going to put money in like a month before you close the account. And that's what this represents here. All right, and now we can just type it in our calculator and you'll get an answer. And I'm not going to share the screen of the calculator, but I'll tell you what this should come out to. Okay, so it came out to $1,277.96. So you made $77 interest versus more versus if you just put $50 in like your piggy bank every month. So that's cool, but I mean, not crazy amount, but you're also only putting in $50 a month, so the fact that you made an extra $77 is pretty nice. And on larger scales for like retirement funds, like if you do this over 30 years and you put like 5-10% of your paycheck in it every month, you can have a really nice lump sum at the end of your career. So definitely, when you are entering the workforce, I encourage you to invest early, because the earlier you invest, the more interest you get and the more money you'll retire with.